Hello everyone, welcome to this tutorial for the RoboWeldAR ROSE-AP software package. In this tutorial I'm going to briefly outline what the RoboWeldAR ROSE-AP component can do and how to install it and how to use it. So what is the RoboWeldAR ROSE-AP? So given a set of photographs of a metallic object that is destined for welding, this module can produce a 3D constructed model of that object along with proposed welding paths. So for this module to work, we'll have to provide it photos of the object, the camera poses in the weld frame, and the module will produce a 3D constructed object and the welding trajectories in the weld frame. And here you can see an example of a dataset that we have provided and the resulting output, so the 3D model along with the welding trajectories in the weld frame. Now we can proceed with having a look at the installation guide. So if I click on this link, that will take me to the installation guide. So in order to run the component instance, we recommend Linux installation, preferably Ubuntu 18.04 or above, and the latest versions of Docker and Docker Compose. You will also need a CUDA compatible graphics card installed on your system and the proprietary NVIDIA graphics drivers. So we can begin with the Docker installation instructions. We have tested this component with these versions of Docker and Docker Compose, and we recommend it to download the latest versions. So in order to get this component to run, you will need to have the NVIDIA CUDA toolkit installed on your local machine, and in order to check whether the installation has been conducted properly, you can, after you run the installation, you can run this command on your terminal and it should produce an output like this. So it should recognize that you have a CUDA enabled graphics GPU. And then once you've done with that, you can then proceed to installing the NVIDIA Container Toolkit, which basically provides access to the NVIDIA CUDA driver on the host machine through the Docker interface. That's associated with the NVIDIA Docker 2 package, and you can download it using our script that we've prepared, and that will install the required dependencies. Also, it's important to note that this component was tested with CUDA 11.2 and the 460.27.04 driver version. So let's proceed with the cloning of the repository. So if you go to the user and programmers manual, click right there. Now this shows up. Here we provide a brief overview of the test files that we provided, the test data set, and the how to clone the repository and how to run the component instance. So of course, first you have to clone your Git repository, and I'll bring up a terminal for that, and I will run this command, and that should clone the repository. I'm going to pause the video now because it takes some time to clone the repository. Okay, so now our repository is cloned and we can proceed with running a component instance. So if we go back to our repository and go to the test documentation, there we will see a description of the directory structure where we provide the raw dataset, the output of the reconstruction module, which is in the mesh directory, and the output of the weld seam detection module, which is in the folder welding trajectory. So we've provided here 3 examples of datasets and their resulting outputs. 2 of them are good, meaning that the image datasets are appropriate, the lighting conditions are sufficient, and the number of data points is also sufficient so that the construction results in a good quality model. And we've provided also an example of a bad dataset, which, as you can see, has less data points and also in which the lighting conditions were variable during photo capture. So that resulted in a worse off model and in an erroneous welding trajectory. For this tutorial, we're going to use the first dataset, which is one of the good ones. So to do that, I will go back to the previous page, the main README, and navigate to the user and programmers manual and scroll down and to the running the component instance chapter. So first we have to make sure we have installed the Docker NVIDIA driver. I have already done that. And the output of NVIDIA SMI from within the Docker instance and from the local, the host machine is outputting the correct output, meaning it's recognizing the GPU on the system. And then the next step would be to set up the services by starting the Docker containers. So now we have to bring up our terminal and navigate to our RoseAP root directory and then into the Docker directory. There we can see our entrypoint.sh script, which we will first give execute permissions to, like this. And now we are ready to run the script. So that started all the services, all the microservices that are needed to execute the functionality of the RoseAP component. And now it's ready to accept requests, meaning it's ready to accept the injection of images in order to produce the 3D construction and consequently the weld seam detection output. So the first thing we're going to do is to run the 3D construction module. However, before we do that, we'll have to install the dependencies. And by that, I mean we have to install the Python virtual environment so that we can run our services to inject the data. So here you can find the instructions. So first we navigate to the source directory. So we go to the root of our RoseApp, to the source directory, and then we can run the command to create the virtual environment. We can use Python 3.7, but even 3.8 is adequate. In my case, I have 3.8 installed on my system. So that just created a virtual environment with Python 3.8.5. Now we can source this environment. And now we are in this virtual environment, and now we can install our dependencies from the RoboWeldAR networking submodule. Copy that. So now successfully installed the dependencies, and now I can run my my data injection scripts from this directory. So to clear that, so we have a clean terminal. Now we can run the 3D construction module, and in the same terminal, meaning under the same Python environment, we have to run this command in order to inject the images into the 3D construction module and successfully start the 3D construction process. However, prior to doing that, we'll have to make a slight modification to this script in order to point it to the right directory, the directory we want the dataset, directory we wanted to draw the dataset from. So to do that, I'm going to use my editor. In this case, a very simple GNOME editor is sufficient. Okay. Now we can change this directory from the default to example files 1, because this is the directory, this is the data that we want to inject. Save it and then close. And now we can run the script. And once I hit enter, this will forward the request to the RoboWeldAR coordinator that runs in the Docker Compose instance. So I hit enter, and we should see now the request being received, and the logger of the process creating a process update for a progress update for each one of the sub-processes of the 3D construction process. So this information, if you have pointed the module to a local or remote Orion instance, will be forwarding this data in NGSI version 2 format to the Orion context broker. So through that, you'll be able to tell when the process is finished. So I'm going to pause the video because in some systems it might take some time, up to 20 or 25 minutes. So I'm going to pause the video now and resume when the process is ready. So now the process is finished, and we can navigate to our root directory of the repository and into the Docker folder. And there you can see that 3 folders have been created. These are the Docker volumes that have been mounted onto this folder. And one of them is the RoboWeldAR coordinator directory. If we go into that, we'll see that there's 3 subdirectories. One of them is the images directory, which contains the images that were uploaded through the data injection script. And you can see both the images and their corresponding NPY files, which contain the welding paths, which contain the camera poses, and also poses.txt file, which contains the poses, the augmented rotation matrices. So if we go back to this folder, once the 3D construction process is finished, the mesh files, the 3D construction output will appear in this folder. Here we have 3 separate files. The first one is the MTL file, which is the material file. The second one is the object file, which is the mesh. And the third one is the texture file, which is has a PNG format. So in order to have a look at these more closely, particularly the mesh file, which is of primary interest, we can use MeshLab, which is a open source software. Drag and drop the mesh file, and that opens up our mesh. The texture in this case has not been properly mapped onto the model, but that's not of a big concern because we're not using the texture. We're only concerned about the 3D topology of the object. So we can remove the texture and have a look at the object without the texture interfering. We can see that the object has been adequately transformed and reconstructed, and with a few artifacts on the sides, which are going to be discarded by the next step of the process automatically. So we can close that window and we can proceed with running the weld seam detection module. So in the same terminal now, we can run this command, which will inject the 3D model, the transformed 3D model, into the weld seam detection module, and the output will be a set of welding trajectories. So let's proceed with that. Let's go back to our terminal. So we can go back to our terminal, copy this command, and run this command over here. This should send the request to the weld seam detection client, and as a result, a model will be produced. And as a result, the weld seam trajectory will be produced. As you can see here, there's some progress, and this request uploads the welding trajectory into the coordinator folder. So now we can go back into our RoboWeldAR coordinator folder and have a look at the folder welding trajectory. There you can see the 3 files that have been generated. First one is a simplified mesh, and that's useful for path planning computations. So it's basically a simplified version of the mesh you've previously seen. It contains less vertices, and it's good for path planning computations in order to get the robot arm at the predefined positions safely and considering the volume of the target. And the other files are the welding trajectory in mesh format, and the welding trajectory in serialized NumPy object format. So we can open this to visualize it. So drag and drop into the same model, and we can see here that the welding trajectories have been successfully found by our model. And that's due to the fact that our dataset is adequate. It's a high quality dataset with many data points and constant lighting conditions. It's useful to note that you might have to run the second step, that is the weld seam detection script, multiple times, because there's a stochastic component in this algorithm that produces the welding trajectories, and therefore may not produce the desired results in the first attempt. With that, I would like to conclude this tutorial, and I wish you happy using of this component. Thank you.